Okay, so we were just discussing the fact that we can't divide by a matrix, so we have to use the multiplicative inverse. And the main point of today is like, how do we find out what that multiplicative inverse is? But first we have to understand some basics. So the first basic is what's in this box, the idea of the multiplicative identity matrix. So basically, if you think back to the numerical example we were talking about, if I have 2 and I multiply it by its multiplicative inverse, also known as the reciprocal in this case, but we're going to stick with the terminology of multiplicative inverse because that terminology is universal for anything that fills this role. We know that the answer is going to be 1, and that's sort of the definition of a multiplicative inverse. What do you need to multiply by to turn this thing into 1? Is everybody good? Yes? Okay. So now the idea is I have a matrix. Its multiplicative inverse, which would be denoted with that same matrix, but then like a power of -1. Just like if you remember in geometry when you studied sine, cosine, tan, and you had sine inverse and inverse sine, inverse cosine, inverse tangent, and they had a little -1 with them. So that little notation of -1 is kind of universally used to mean an inverse, okay? It's used with functions, it's used with matrices, it's even used with numbers. So this means a matrix times its multiplicative inverse. You have to get something that's the equivalent of 1, but for a matrix. Now this is different than a zero matrix. Remember we learned about the zero matrix the other day. A zero matrix is just full of zeros. The identity matrix is different. The identity matrix has 1s on the diagonal and 0s everywhere else. So only a square matrix can have an identity matrix. There's no identity matrix for like a 3 by 2. There is for a 3 by 3 and a 4 by 4 and a 5 by 5, et cetera, et cetera. Has to be a square matrix or else there isn't an identity matrix. It just doesn't exist. This is one of the issues with why we don't have division, right? Operations have to be something you can just sort of always do. The only time we can't divide is we can't divide by 0 when we're talking about the number system. But with matrices, you can only rarely do this thing that would be equivalent to multiplication. It's only with square matrices, okay? So it's so limited, it wouldn't have any meaning to talk about being able to divide. Question, Rachel?
So when it would be a 3 by 3 matrix,
Matrix.
it would be just like the entire diagonal, not just the corners.
Correct. So if I had a 3 by 3 matrix times the inverse of that 3 by 3 matrix, I would get this. And we've actually seen the identity matrix before. If you remember when we did RF, we did it on like a 3 by 2 by 3? No, 3 by 4. Remember that? Yeah? And you would get the identity matrix and then some numbers, right? So this part here was the identity matrix with a constant matrix attached to it. Are we okay? Yes, okay. So the short version of this is if I multiply a matrix by the appropriately sized identity matrix, I'll just get the same answer I started with. And if I multiply a matrix by its inverse, I will get the identity matrix. Are we good? Yes? Okay. So this gives us a test. This is how we test to determine whether or not two matrices are inverses, which isn't something we'll do a whole lot, but it will come up in the lesson 7 daily practice that you're going to do tonight, okay? So you will see a question where they say, here are two matrices, are they inverses or not? And then you'll have to explain how you know whether they are or are not matrices. So here we have two matrices. Now the first thing you should notice is that these are bigger than 2 by 2. Do you have to multiply things by hand if they're bigger than 2 by 2? No. So for our purposes, this is going to be a calculator problem. In addition, I'm going to show you something that you actually saw in a calculator activity already, but it's the not shortcut way of working with matrices. And the reason we're going to do it is because we're going to use A more than once. We're going to use B more than once. So that alpha zoom shortcut that puts the matrix right on your screen is not a great choice if you have to use it multiple times. Better to store it under a particular name so that you can just go grab it again when you need it. Does that make sense to everybody? Yes or no? Yes? Okay. So the first thing we're going to realize is it says if matrix A and matrix B are going to be inverse matrices, then it has to be true that if I multiply them first A times B, and then also if I multiply them B times A, I will get the identity matrix both times. Is everybody with me? Now, why in the world would I need to multiply them in both directions? What's up with this, Will?
Because with matrix equations, you multiply them in two different orders to get different things. It might not be the same.
Okay, so typically matrix multiplication is not a commutative process. The order does matter, unlike with numbers. So in order for these to truly be inverses of each other, it has to work in commutativity. It has to work in both directions. Everybody good? All right, so you're going to go into your calculator and you're going to use second x to the negative first to get into the matrix menu. From there, you're going to choose edit and you're going to put the first matrix into matrix A. Then you're going to use second mode to quit out of there, and you're going to repeat the process to put the second matrix in matrix B. Okay, so if I go look at that, I've written down the steps for you. There's my calculator. I would do second x to the negative first to get into the matrix menu. I would go over to edit, and I would choose matrix A. From matrix A, notice this one is currently the wrong size. I need a 3 by 3 matrix. So I'm going to tell it that I want a 3 by 3 matrix and hit enter, and it sizes the matrix appropriately. Then I'm going to take matrix A and I'm going to put it in there. So I've got 2, 0, 11, 1, 3, negative 1. Make sure to use a negative and not a minus sign because your calculator will get mad at you. The computer calculator is a little slow. Now, unfortunately, there's no handy back button like on a computer. So you actually have to quit out of here and then go back in. But this time when you go to edit, you're going to choose the second matrix. And you're going to make that one a 3 by 3. And I'm going to show you the first cool thing. Now, we've seen this before. If I want to put in fractions, I want to put them in looking like fractions. So I've shown you before that you can do alpha y equals and choose number 1. And that makes the fraction symbol. So now I can do 4 over 3. And it puts it in looking like a fraction. Does that make sense to everybody? Yes.
Would you rather have us do that than have it be like decimals?
You do not use a decimal. You're going to end up rounding off, and then it's not going to be correct. Does that make sense? So if I don't give you a fraction, I expect that you are not using a fraction. And you will find, if I don't give you a decimal, I will expect that you are not using a decimal. You will find that if you use a decimal when you should not, you will not get full credit for your work. So you want to be in the habit of using the fractions when they are given. The only time decimals are okay is if the decimal was already in the problem or if the problem is about money. And then it would be logical to use decimals.
Or if it's in like something that makes a decimal.
What makes a decimal that doesn't make a fraction?
Sine/cosine.
Sure.
And also rationals.
No, you would leave an irrational in its simplified irrational form. Because otherwise you'd be rounding that off to put it in. The whole point is we shouldn't be rounding numbers off in our work. We should be using exact numbers in our work. All right, so we get our whole matrix in there. And then you quit out of there. So both of your matrices are stored. So now we're going to have a couple things to do. First, we're going to need to do A times B. So matrix A times matrix B, and we're going to get an answer. So to do that, you call them out by name. So you want to be on the main screen of your calculator. You're going to do the second matrix to get into the menu, and you're going to choose A because you want to take matrix A times, back into the matrix menu, and you want matrix B, and you hit enter, and the calculator does all the fancy work for you. And you see that you get something like this. Is that the identity matrix? No, this is not the identity matrix. All right? So, in this case, do we even need to try B times A? No, why not? Yeah, it has to work in both directions. If it doesn't work in the first direction you try, you don't even care if it works in the other direction. Does that make sense to everybody? Yeah? So, we could try B times A. I will tell you it's also not the identity matrix. But we really don't even need to try the second one. You only need to try the second one if the first one worked. Does that make sense to everybody? So I would need to explain, though, because knowing how to push buttons on the calculator is great, but actually understanding what that all means is what I actually care about. So when you answer a question like this, I would see your work that you did A times B, and you were like, well, that's not the identity matrix. So you wouldn't even waste your time doing B times A. You would just say, since AB, right, the product of matrix A and B, is not the identity matrix, they are not inverses. So that would be my answer, but I would have work to back it up. Are we okay? Rachel?
Do you want us to write out the identity?
You can either write out the identity matrix. I did it here because it's new and I want people to be realizing what the identity matrix is. The other notation I would accept in this case would be the capital I sub 3 by 3, right? Because I want you to realize that you're looking for a particular identity matrix, not just any identity matrix in general. Is that okay? So either of those would be acceptable to me. Any other questions? All right, next. So there's this thing called a determinant, and it's the next thing we need to talk about because it's one piece to the puzzle of coming up with that multiplicative inverse matrix that we have mentioned already today. So the determinant, I think the easiest way to talk about it is to call it like a score. So does anybody have like little brothers and sisters that are way younger than them, like a lot? Okay. So if you have a little brother or sister that's so much younger than you that like you remember when they were born, yeah? Okay. You may, but maybe not, because it's kind of a grown-up thing, have heard of something called an APGAR score. Has anybody ever heard of an APGAR score? Yeah? So an APGAR score is something that nurses and doctors who work with babies being born are very familiar with. It's basically a score that they give to the baby. You're like, really? You get born and you like immediately take a test? Sort of. Okay, so basically the APGAR score tells the doctors and the nurses kind of a quick snapshot as to the health of the baby and what they need to do with the baby next. Okay, so the baby's born. Ideally, they just hand the baby to mom and everybody's happy, right? Sometimes when babies are born, there are issues, like they might have trouble breathing or they might be severely jaundiced, which can be very unhealthy if it's not treated. There's lots of things that can happen. So basically, when the baby's born, either they immediately give the baby to mom, or especially if they notice a problem, they're immediately going to test the baby on a series of different things. And I'm not a doctor or nurse, so I don't know what all the things are. But they're testing for things like reflexes, ability to breathe. The color of the skin. If a baby is very yellowy in their skin tone when they're born, like most babies come out pretty red, but if they're very yellowy in their skin tone, they have a lot of bilirubin in their blood, and it's not healthy. And so there's special lights that they put the baby under, and it helps the body to clear the bilirubin out, and their skin goes to whatever tone it's supposed to be. That's not yellow, okay? But it's something that's not healthy for the baby if it goes untreated. So they have all these different things that they score the baby on. All right, so they score the baby, and based on like different categories of where that score is, it's either, okay, just give baby back to mom, or it's baby needs to go straight to the NICU, or baby needs to be on this, or whatever it is. So it's this ranking that quickly then tells the doctors and the nurses on a big picture scale what needs to happen next. Does that make sense to everybody? Okay, so the determinant is the APGAR score for the matrix. It will tell you, based on a number, the number is either in one category or the other. And depending on which category the number is in, it tells you what you can do with that matrix. Does that make sense? Yes? All right. So there's a lot of things with matrices that fall under the like heading of just do it. Don't stress about why it works this way. It will not improve your life. Okay? This is a procedure. We're going to learn to follow the procedure, because unless you're going to take an entire like semester-long course dealing with matrices in college, you just don't have the like background to really get why it works. It's just that it does. Is everybody with me? Yes? You will find it's rare in Algebra 2 that I ask you to just trust me that it works this way, but it happens a lot with matrices, okay? Because you just need a lot more background than what you have right now. But you can learn to do things with matrices that make other bits of math easier, so it's worth learning it even before you can understand the whys. We just learn the hows. So there's this little process to come up with the score. Now we're going to put a star next to the first thing, because for the first part of this, that's something you're going to have to know how to do by hand. The bigger ones, look at all the extra rows and the crazy diagonals. I am not going to make you learn how to do that by hand. You're going to let a calculator handle that stuff, okay? When I was in school, we had to do it by hand. You guys get the easy way. You get to just do it on a 2x2. So first, in 2A, it says, what is the determinant of? And you go, ooh, that's a 2x2. I have to do this by hand. So the first thing you're going to do is write down the appropriate notation. We're doing the determinant of the matrix 2, 3, 4, negative 5. That's what the notation looks like. And then it's a process to create a score for the matrix. And I'll tell you what the score means after we find it. So the process looks an awful lot like cross multiplication for solving a proportion. So if you think about having a proportion back in geometry, you would take the product of these two and the product of those two. Now in a proportion, that would then create an equation. For us, we just subtract them. So I'm going to say 2 times negative 5 is negative 10. 3 times 4 is 12, and I'm going to subtract them. What do I get? Negative 22. So the score for this matrix, the determinant of this matrix, is the number negative 22. So this question doesn't actually ask us about it, but I find it awkward to talk about a determinant without telling you what it does. If I can't tell you why it does what it does, I can at least tell you what it does, okay? So what it does is tell you whether or not there's an inverse, because not all matrices even have an inverse. So in order to even be eligible to have an inverse, it has to be a square matrix. And then when it's a square matrix, we have to calculate the determinant. And as long as this is not equal to 0, it does have an inverse. If I calculate a determinant and I get 0, I don't need to do anything else trying to calculate an inverse because it doesn't exist. Are we okay? Yes? All right. So then in 2B over here, I see a big matrix. Do I have to do that by hand? No. So we're going to practice our calculator a little bit more. On our paper, we are going to write, I am finding the determinant of this matrix. This is what the notation looks like. But then I'm going to go to my calculator, and I am going to type it in. Now, I need to know where the determinant function is, right? That is a function. It's in that matrix menu again, right? So I'm going to clear out what's on my screen, so I don't have anything there. I'm going to hit second matrix to get in there, and I'm going to go to math. So I'm doing second x to the negative first to get into the matrix. I'm choosing the math menu because that's where the operations are. And notice the very first one is determinant. Okay, so I'm going to choose the determinant. Now, since I'm only going to use this matrix one time, I'm going to use my shortcut keys and put the matrix right here on the screen. I'm going to choose alpha zoom. I want a 3 by 3 matrix. Conveniently, my calculator is ready for that, but you might have to adjust the size on yours. And then using the arrow keys, not enter, bless you, to navigate around, I'm going to go ahead and enter that matrix in. Oops. Once you have the whole matrix in there, you can push enter, and it will calculate the score for you. Does this matrix have an inverse? It does, right? Negative 10 is not 0, so this matrix does have an inverse. All right, any questions about the how, of how we calculate a determinant? Or the what of what it tells us? We're okay? All right. We're going to skip over number 3 at the moment, straight to number 4. It flows a little bit better. I'll come back to word problems in a slightly different order afterwards. So now we're going to follow up with this determinant. So we actually care about the determinant because we care about finding inverses. The determinant by itself, not super useful, okay? But here off on the side, there's this thing, it says, let A be the matrix A, B, C, D. If the determinant of A is equal to 0, then A is a singular matrix and has no inverse. We were just talking about that a minute ago. And then down below it says if the determinant of A is not equal to 0, then the inverse of A, which is denoted as A to the negative first power, using that not as a true exponent but to mean inverse, is 1 over the determinant of A times this crazy modified matrix. So it's actually not as crazy as it looks. There's sort of a definable pattern here. So if I'm over here, the very first thing I have to do is figure out if it has an inverse. So first I'm going to find the determinant of the matrix, and since it's a 2 by 2, I'm going to go ahead and do that by hand. So I write down determinant of the matrix is equal to the first diagonal product, which is 24, minus the second diagonal product, which is 12. And so what's our determinant? 12. So does it have an inverse? Yes. So we're going to say yes, the determinant of this matrix is 12, which is not 0. So it does have an inverse. Since it has one, we need to calculate what it is. So we follow the formula. So the inverse of this matrix, so this matrix denoted with its inverse, so that's that negative 1 looking like a power, it's 1 over the determinant. We already figured out that the determinant was 12, so conveniently we get to use that number again. Times a modified version of this matrix. So the first thing we need to do is swap the upper left element with the lower right element. So the 4 and the 6 are changing positions. Are we okay? So they switch on the diagonal. Then the other 2 stay where they are, but you give them the opposite signs. So whatever sign they have now, they get the opposite sign. So in this particular problem, they both become positive. Then you notice this is a scalar multiplication problem. Is everybody with me there? Yeah? Okay. Now, I would certainly hope you don't need a calculator to do this. We're just going to do it by hand. But then I'm actually going to show you something cool in your calculator. So first, let's do it. What's 1/12 of 6? 1/2. What's 1/12 of 4? 1/3. What's 1/12 of 3? 1/4. And 1/12 of 4 again? 1/3. So we're going to look at a couple of things once we've written that down. Does everybody have that written down? Yes? Okay. Yes.
So that 112 comes from what again?
The reciprocal of the determinant. Is that okay?
Yeah, it makes sense.
Yep. So the 1/12 is the reciprocal of the determinant. All right, so we're going to look at a couple things. First of all, we know that if it's a 2 by 2, we are required to do it out by hand. But if it was bigger, you would be allowed to use a calculator. And I didn't put a problem on the note sheet that's bigger, so I'm just going to show you how to do this in the calculator on this particular one so you can verify that it comes out the same. Everybody okay? All right, so grab your calculator, clear out anything that's on the screen. So the original matrix was a 2 by 2. So I'm going to go in and make a 2 by 2 matrix on my screen using that shortcut key because this is not a matrix that I have to reuse. Single-use matrices I usually do this way. All right, so then you put in the original matrix. And then you go outside the matrix and you say, well, the notation for this to get the multiplicative inverse is that exponent of -1. So you use the x to the -1 button to get that little exponent of -1. Is everybody with me there? So that one's kind of nice because you don't have to go deep in any menus to get it. It's just right there. Then you hit enter. And you go, uh-oh, Mrs. Leonard doesn't want this, right? Because see all those decimals? Now, these decimals happen to be ones that I would think you would recognize their fractional equivalents, right? They're perhaps the most common fractions that we ever see. But in case you didn't, I want to show you something. Just a second, Lucas. Just a second, okay? So in case you don't know this trick already, I want you to know that you can do this on the entire matrix, but this also works on individual numbers, okay? So anytime I want it to take the answer I just found a moment ago and do something to it, I don't have to go get that or anything. If I just start typing, it's going to assume I'm performing this on the previous answer. So what I wanted to do is change this into a fraction. So I'm going to go to alpha y equals, and see the fourth option says convert between fractions and decimals. So I'm going to choose the option and see how it says answer fractions to decimals. So that means it's taking the answer to the previous problem and performing this operation on it. Hit enter. It did the whole matrix at once. Is everybody okay with that? Aren't you happy I showed you that clever trick? Lucas, is that how you were going to do it?
Actually, you can get access to just, if you press math, it's the first thing. You can just press math and then.
And fraction to decimal is also buried in that menu. Yep, absolutely. Well, that's just how you get a fraction. I don't think that's how you convert back and forth. Oh, you can too? Oh, nice. It uses both ways? Perfect. So there's two different ways to get to the same menu. We good? All right. So that's A, how I can get an inverse of a bigger matrix using my calculator, and B, how I can get it in a format Mrs. Leonard will accept, because you know I don't want to see decimals when that come out to be a decimal. All right, ready for the word problems? Yes? All right, so first we're going to do this one. This one's kind of funny. This is like you're a retired math, you miss doing math, so this is how you do things. Normal people don't do things this way. But this is how coding was once done. Now coding is way more sophisticated than this. But this is one of the fundamental methods of how you can code something. So this says you stored your credit card number in a file after they were coded by this particular matrix. One of the numbers in the file is -1, -14, blah, 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 okay? So that's not the actual credit card number. Like if you've ever seen a credit card, I'm sure you realize there are no negative numbers on credit cards, okay? This is the coded version of the credit card number. We're asked to figure out what was the original credit card number. So now we have to think about this. The original credit card number was encoded with this matrix. If we're going to decode it, can we use this matrix? We have to use the inverse of this matrix, the multiplicative inverse of this matrix. Does that make sense? We also have to take the credit card number and put it into an appropriately sized matrix. See how the matrix is 2 by 2? Our matrix has to have a dimension that involves a 2. Does that make sense? So usually we do it this way. We take the matrix inverse and we multiply it by this one. So I think this is going to have 2, 4, 6, 8, 10, 12, 14, 16. Yeah. So we're going to make it a 2 by 8. And the order that we put it in, uh-oh, I missed a number. Oh, there's 2 negative. No, I missed a number. What did I miss?
No, you just didn't put it's just 370.
Oh, that's interesting. I don't know why I thought I was off. All right, so I have a 2 by 2 times a 2 by 8. So those are compatible dimensions. Is everybody with me? Yes? So the order that I put it into the matrix needs to be the same order that I take it out of the matrix. So if this is a 2 by 2 times a 2 by 8, these match, so the multiplication is possible. The dimensions of my result will be those exterior dimensions, right? It's still going to be a 2 by 8 matrix when it comes out. Everybody good? All right, is that the kind of matrix I make you do by hand? Nope. So you're going to type it in exactly the way you see it up there. Don't forget to take the inverse.
So we don't even have to make the inverse. We don't even have to convert the inverse.
No, I'm being kind. Look how nice I am. So basically the idea is the point of this problem is not to make the inverse. The point of this problem is to know that the inverse is what you need. Do you see the difference? So since it's just one step in a word problem, I'm not testing your ability to do the inverse. I'm testing your ability to know when to use the inverse. It's a different kind of thing. So once you get it all in there, tell me how it turned out. My computer is not cooperating. I'm trying to get to my thing so I can pause. Uh-oh. Well, that's decidedly inconvenient.
Okay, I got a lot of numbers.
Hold on. Mike decided to mess itself up. Okay, I think that's back where it ought to be. All right, did you see numbers for me?
I have a lot of numbers.
Okay, so tell me the matrix that you got as your answer.
I can't see all of it.
You should be able to arrow off to the side.
Well, I can read to you what I have.
Okay.
I have 2, 4, 5, 5, 1, 1, 8, 7. And then the 3, 2, 3, 1, 5, 5.
3, 2, 3, 1, 5, 5,
3, 2.
3, 2. All right, so that means the credit card number was 2455 1187 3231 5532. Okay? All right. Oh, come on, computer. Here we go. I'm going back up and doing number 3 because we kind of skipped over it because I just don't like the flow. So I'll tell you, this is one of the most contrived problems I've ever seen in my life. And you will absolutely not be expected to know this formula. There will be a homework question that uses this formula, but the formula is in your book, so you can find it there. Everybody's good? And it's on your note sheet because I put it here. So it says, the area of a triangle with these 3 vertices, so it's a triangle on the coordinate plane, you can calculate its area with 1/2 times the absolute value of, the absolute value of the determinant on the matrix where A is equal to basically the coordinates and then an extra column of 1s to make it a square matrix. Potentially the most random thing I've ever seen. So what you need to understand is that some people just really love math for the sake of math, and it's like their job to look for mathematical relationships. So someone who has time to think about these things discovered that this works, and they proved that it works. And the makers of your math book were like, we need some sort of application. What can we find? Ooh, that's an application. So without regard for the fact that this is one of the most useless formulas I've ever seen, they decided they would show you how applicable this is. Does everybody understand where we're coming from on this problem? Okay, I'm not pretending like I think this is practical. All right, so here's the deal. It says, as part of a remodeling project, you want to paint a triangular area on a cement floor that is marked along the wall with decorative stones conveniently at every meter. Using the stones as a reference, you determine the coordinates of the vertices of the area you want to paint are 4, 6, 12, 9, 7, 11. What is the area of the triangle? So we create a 3 by 3 matrix by creating a coordinate matrix and adding a column of ones to make it square. Everybody okay? Then we do scalar multiplication basically on the inverse here. So we're doing 1/2 times the determinant of that matrix. And because this is a big matrix, we put it in our calculator. So grab your calculator. On your calculator, you're going to type exactly this in. You're going to do 1/2 times, and then you're going to go into the matrix menu and grab the determinant function, and then you're going to put a 3 by 3 matrix on your screen and type it in. I'll tell you that you're going to get 15.5. All right, your daily practice tonight is the lesson 7 daily practice.